Okay, so I hope that's visible. Let's start recording the session. Perfect. Nice. Okay, so intro to binary exploitation. I specifically chose this topic for a reason. First, I have little experience working with binary exploitation and low-level stuff. So choosing this would mean that I would have to go there, research, and present others an opportunity to actually learn along with me. So let's get right into today's session. This is our agenda. Most of it will be practical, and the prerequisites for today's session will be very simple. A basic Linux understanding and the ability to read code. In the introduction, we'll talk about what binary exploitation is, how you can read C code, and develop simple exploits with Python. We'll then move on to discuss the stack and registers and how it plays a key role in execution of programs. We will move on to, I think, introduce Linux buffer overflows, where we'll see how to exploit simple programs. Within the buffer overflows, we'll cover shellcode injection and then finish off with how to mitigate against these exploits. I'm not sure if time will allow us, but I'll try to do all this within an hour. Okay, so first of all, why is this topic even relevant? Okay, it's a good starting point for learning vulnerability discovery and exploitation. Before we even ask ourselves what binary exploitation is, we need to know what a binary is. And simply put, it is compiled code that gets executed as a program. In Linux, we have them as ELFs, executable and linkable format, and Windows has PEs. So if you've already guessed, binary exploitation refers to the process of taking advantage of flaws in how code has been written to cause unintended behavior. So with that short intro, we will see how we can read and interpret simple C code. I'll show you in the lab. And for this, you do not necessarily need to know how to write C code, but preferably have a background of writing code in other languages like Java, C++, Python, JavaScript, and all that. So because we will be looking at functions, loops, passing parameters, and we'll see all this in the first lab. So before that, I'll shortly talk about some of the tools that we need for most of these operations. Okay, you don't need all of them, but there are some that are really good if you want to maybe speed up the exploit dev process and make the procedure easy. We have Pwn tools. This is a powerful Python library. It's used in exploit development and mostly CTFs. We have the GNU debugger, or GDB in short. It's a powerful Linux command line tool. You can use it to debug and reverse binaries. You'll be seeing that. We'll be using GDB for this. We have R2. R2 is a framework for reverse engineering and analyzing binaries. We have Metasploit, which most of you are familiar with. It comes into play in different ways. We'll see how. We have Anger. It's a Python framework for reversing binaries. Also IDA, reversing, and ROPA is, okay, this is, I think, out of scope for this session. And since this is a beginner lesson, we'll focus, I think, only on GDB. I wanted to showcase Pwn tools, but I don't think we'll have time. So this brings us to the first program that we'll be exploiting today. In this program, you'll see how you can break the logic of an application and cause the supposed unintended behavior that we mentioned. So you can start by heading over to, I think I have it here. I need to hide this thing, it's distracting me. You can head over to pwnable.kr. How do you take off this thing from here? So Pwnable.kr is an awesome site for learning basic to advanced binary exploitation techniques. It showcases some Linux concepts like file descriptors, the stack, and heap exploitation. We also have return-oriented programming and etc. So you can log into this site or register rather. So for today, we'll be doing the collision challenge, or rather for the first lab of this session, we'll be looking at collision. So from the challenge description, you can see that it says, Daddy told me about cool MD5 hash collision today. I want to do something like that too. So one of the properties of a cryptographic hash function is collision resistance, meaning no two hashes can be the same. So we'll SSH into this server. And you'll see what I'm talking about. So in this challenge, you'll be required to create a hash collision and bypass a password verification check. And you'll see how we can do this. I think the password is guessed. Okay, so if you list the files that are in the server, you'll see 3 files: a flag file, call.c, and call. Call.c is a C file, basically a file written in C or a program written in C. And when you compile it, you get call. We also have flag, which in this challenge, our goal will be to read flag. And you'll see how. If we try to read flag by simply cutting out flag, it will tell us that permission has been denied. And why is that so? Because the person who has read access to the flag file is not us. We are call, and call_pon has read access to the flag file. So what do we need to read the flag file? We need some kind of maybe permissions, or maybe bypass some checks that will allow us to actually read this flag file. So if you try to run this call binary, it will tell us that you need to supply a passcode. And if you try to supply a passcode for it, maybe like 4As, it tells us that the password length should be 20 bytes. So let us try put 20 bytes into that. So we put 4As, basically 1A is 1 byte. So let's try putting 5 of this 4As, 1, 2, 3. 1, 2, 3, 4, 5. Yeah, so this is 20 bytes, but it tells us that that's the wrong passcode. So we can try investigate further by looking into the source code. Nice, so you have this. It's not as complicated as it looks. So I'll try break down the logic of the C code for you. We have a main function, and you have a check password function. We also have a hash code variable that has a hexadecimal value in it. And in the main function, we have blocks of if statements that validate the input of the program before passing it to the check password function. And if we pass the correct password to this file or the compiled binary, we'll be able to get the password, or rather the value of the flag that you aren't able to read it, because it executes a bin cat command on the flag file. Otherwise, we get a wrong passcode. So in the first if statement, it tells us that this passcode needs to be 20 bytes long. And this is our first hint in the program. Okay, not much of a hint, but most of the time, if not always, integers always occupy 4 bytes in memory. So if it tells us over here that we need 20 bytes, this means that we need 5 integers, because 4 bytes equals to 1 integer. So what about 5? In this third if block, it sends our passcode to the check passcode function, this one, check password, sorry. And if the result of the function is equivalent to the hard-coded hash code, this. So if the hard-coded hash code equals to what we pass as a parameter in the command line, the program prints out the flag for us. So inside this check password function, we'll see that it takes a string as an argument, and then you have a pointer variable called IP, which stores the location of the variable you pass into the function, this. And the for loop basically helps us perform some pointer arithmetic. So remember that I told you that 20 bytes will equal 5 integers. Well, for this loop, it treats the input like 5 integers. It breaks it into 5 integers and adds every 4-byte chunk to its other. Like if I have maybe 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, they'll all be added to each other recursively. So this logic actually took me a while to grasp, so don't worry if it seems a little bit tricky at first, but the workaround is pretty simple. Because now that we have this hard-coded value, we can create our hash collision by splitting this value into 5 different integers, which will be in hexadecimal, and pass them to the program. So if the integers get added up, we end up with the value of the hexadecimal hash code and bypass the password check. So we'll start by actually developing our exploit for this, and we'll use the Python idle terminal, this one. Oh, we need that value. Let me just quickly copy that. I'll work from my side. So if you type this out and press enter, you'll see that it gives you its value in decimal. So this hex equals to this in decimal. So what do we need to do? We need to split this value into 5 different chunks. And when these chunks get added up, they'll get added up to this. So that's very simple maths. So if you split this up into 5, you'll see that it's not perfectly divisible by 5. So all we need to do is get this value and then the value that remained after our division. So this divided 4 times, and then we got a certain remainder. So if we multiply this by 4, and subtracted it from this, we get the remainder. So this is the remainder. So if we do this multiplied by 4 and add this, we have 5 different integers. And these are the integers that we need to perform our hash collision. But we need them in hex so that they get converted back to an integer value like this one. This will get converted to an integer value. So we need these values in hex, this value and this value. So the value of this in hex is this. And the value of this one in hex is this. Ooh, someone annotating. Okay, so we need 4 times of this and 1 of this that we got here as a remainder and pass that as input to our program and see if we'll be able to bypass the check. So if you take this, multiply it by 4, and then you take this, you get a value. Okay, so I think we need this in hex and not as integers. Yeah, so we have this long string. So we try pass that as input to our program and see what happens. So if you pass this, okay, we don't bypass the check. It tells us that the password length should be 20 bytes still. I don't know how many bytes these are. This is 1, 2, 3, 4 times 4, that's 16, and 4 of this. Let me try remove, oh sorry, let me try remove this. Okay, so for one, the reason why this won't work, I'll show you why. If you were to type ls CPU and grep for something called a byte order, it will tell you Little Indian or Big Indian, depending on your system, but most of them are usually Little Indian. What this means is that the order of the bytes that you're passing into your program matters. So if we pass in bytes in the wrong order, let's say in Big Indian. Big Indian means, I think, let me just quickly search that up for you. Yeah, so endianness is the order sequence of bytes of a word in digital data in computer memory. So Little Indian means that the order of the bytes is reversed, while Big Indian means the order of the bytes is the same as it's supposed to be. So in our case, we're actually dealing with Little Indian. So passing the bytes in like this won't work. So we have a really cool module in Python called the struct module, and it helps us actually reverse bytes, pack them in a way that the program will be able to understand. So I think I'll just throw this inside an exploit script instead of working from there. So we'll begin by importing the struct module. And then we have our first chunk. Let me call it first chunk. And our first chunk of bytes was this. So what we do, we pack those bytes in Little Indian such that they get reversed. And our second chunk was this. So if you were to print, let's say the first chunk, I want you to see how that will look like. I hope I don't have any typing errors there. Okay, they get printed in this unprintable manner, but it should get reversed on our other side. Yeah, you see it like this. It gets printed backwards somehow. The C8 starts, then the CE, and then the C5, sorry, the 5C, C5, yeah, and then the 06, because we have 0 from, I think, the beginning. So now, as we interpreted the first logic, we multiply the first chunk by 4 and add the second chunk. Although I don't like the way it gets printed out like this, I want them in bytes, in the actual printable bytes like this. You can still work from the idle terminal. Let's just pack those bytes from here. So you want to take the first chunk 4 times, and then the second chunk. Okay, I'm not sure if this will work because the bytes aren't really getting printed the way we want. But let's just try pass that to our program and see what will happen. If it doesn't work, we'll have to use Python directly from here. I'm really sorry for this hit you're having right now. So I think let me just try this with, using pawn tools instead. So you see how the bytes are being printed, and we'll actually get to see how another tool is being used to solve this challenge. So if you're going to use Pond tools to actually solve this, okay, the problem I'm having is how I'm printing out the bytes. And okay, didn't really anticipate to experience this during the presentation. So I'll try to actually fasten this up by showing how Pond tools is used in this. First, we start by by importing Pond tools. And then we can create a payload and pack the bytes in 32 bytes, in 32 bit. I think if we do a file on call, we'll see that it's an 32-bit ELF. So if we pack the first bytes that we had, which ones are they? These ones. And then let's add the second chunk. Ooh. Okay, let me print this. I see if it will look better. Okay, I think this is much better. We can SSH into the server remotely by providing the username call. We can provide the name of the site, and we can provide the password. And the port, we are going in through port code 2, I guess, 2222. And then we create a process using the session that we've engaged with the server. We can pass in the name of the executable, which is call. And you saw that call was, I guess, taking in payload. Taking in an argument. So we supply it as an argument vector. And then we try receiving the input if it works. If it doesn't, well and good, I'll try proceed further to the binary exploitation part. The buffer overflows part. Okay, so that worked. I'm not sure why we are getting the bytes issues with our program, but our calculations are correct. If we split that up into 5 chunks, 4 bytes each, we are able to actually print out the contents of the flag. So sorry for that little hitch. And I can see I've eaten up the time a bit, but I'll proceed with the buffer overflows part. I hope I'll be able to show you what I have for that in practice. So that's an example of how you can break the logic of a program and bypass some simple checks. Okay, so I'll move on with the slides. Okay, so now we have a section covering a very important thing in memory, stack and registers. So we'll start. The stack is a last in, first out data structure, as most of you may know. Like a stack of plates, elements are usually added to the top. And to remove elements, you take the top element out first. So these two operations that I've said are known as pushing and popping data. Also, something very important to note is that the stack grows backwards, the stack grows backwards into memory. So when we add elements to the top of the stack, the memory address keeps going lower and lower. So it goes lower towards the top and higher towards the bottom. So that's why we say it grows backwards into memory. When functions are called, like you can see here, when functions are called, the return address usually gets pushed onto the stack first. Like look at this first section over here. Return address will get pushed first. Return link to n-3. And then we push the local variables and then the arguments that maybe this function will be calling. And this single part is what we call a stack frame. As you can see in that diagram. So the return address that I'm talking about is basically where the stack will return the control flow of the program with help from the instruction pointer. The instruction pointer that I'm saying is basically a register that is used to point to the next instruction to be executed in memory, which is where memory execution usually continues to after calling the function. So if I call the function and its data is placed onto the stack needs to know where it's going to return to the program once execution continues. We have the base pointer, which points to the bottom of the stack, and the stack pointer, which points to the top of the stack. So those are very important registers that you need to keep in mind for the rest of the session. The instruction pointer, the base pointer, and the stack pointer. Stack pointer points to the top of the stack, base pointer to the bottom, and the instruction pointer to the next instruction to be executed in memory. So these registers that I'm mentioning help us to hold data for execution of programs. We focus on 32-bit and 64-bit. 32-bit means it can store 2 to the power of 32 values, or rather data is represented in 32 bits. The same goes for the 64-bit ones. So the important registers we'll be going through are those that I've mentioned. And in this case, since you're working with 32-bit for now, we'll be doing the ESP, the EIP, and the EBP. And we'll see how we can use the instruction pointer to point to malicious code and get it to execute something that you want, preferably for now, a shell. So now for the practical part of this session, we have the buffer overflows. So I'll start by defining what a buffer is. A buffer is simply an allocated storage space in a program. And an overflow occurs when the input exceeds the amount of space that has been allocated by the buffer. So I have this oversimplified diagram that shows if we allocated 8 bytes of space for input and receive 10 bytes instead, that causes a buffer overflow, an overflow of 2 bytes. We also have this diagram over here where we have the vulnerable string copy function in C. I'll show you in the Linux man page. If you go down here at the bug section, you'll see that it tells us the string copy function does not have any form of bounds checking. You cannot really tell in future how many bytes are being copied. So you won't really be able to put some bounds, and this causes buffer overflows. So since it does no bound checking, hence allowing us to supply larger input than the buffer, it causes a buffer overflow. So this brings us to the question of what is the severity of this bug? Well, it can go on to crash programs, servers, and cause arbitrary code execution, which is like the worst of all, which is what we'll be looking at in future. So here we have some simple steps that we'll use in exploiting our program. Host, could you please mute our person? Okay, so I was talking about the steps that we'll be using to exploit our program. But for us to first perform the buffer overflow, I want us to understand how registers will look like in execution. So say, in this example, the function gave us a buffer of 100 characters, the buffer space to use maybe 100 characters only. And we send a bunch of A's to the server. Say we send 100 extra or 1,000 extra ones. What happens in this diagram is that they get correctly sanitized and they do not escape the buffer space. Thus, no buffer overflow occurs in this diagram. But here, the A's completely escape the buffer space and they reach the instruction pointer. So this is very dangerous, since if we gain control of the instruction pointer, we can use it to point to malicious code and get code execution that we'll see in the next lab. So for this lab, I think I have some credentials over here that, let me just copy this to the chat. So if you're going to follow along with me, or let me also copy the exploit that we wrote in Pawn Tools. I think I went a little bit too fast there because of an anticipated issue. If you get to install Pawn Tools on your machine, you can try run this code on it. So we'll start by looking at the Narnia 2 challenge from the Narnia War Games. We'll use Over the Wire. Over the Wire is a really amazing resource that you can check. And they usually provide these war games. War games are like retired CTFs, I guess. And they can help you learn and practice security concepts in form of fun-filled games. This is how I actually got to start learning how to hack and all these kinds of security stuff. I started with Over the Wire. So we'll be looking at Narnia. Narnia is really interesting. It talks about, I think, binary exploitation in depth, and you can see some ways to learn basic exploitation techniques. So just SSH into this server. Okay, now that we're in, you can cd to the /Narnia directory, and you'll see that we have compiled binaries inside and their respective C code that you can look to. So we'll be looking at the Narnia 2 challenge. So if you run Narnia 2 like this, ./Narnia2 tells us that it expects an argument. So let's just supply something there. Be something like Nancy, and Nancy gets echoed out to us. So from that very shallow analysis, you can tell that our binary is accepting input and giving it us an output, the same thing. So if we were to look at the source code, we'll expect something similar. And you'll see that we have a buffer declared with a size of 128 bytes and a string copy function over here. We have a string copy function which does not have any boundary checks. So it copies input that we supply as an argument, argv. This means that we are supplying input to the program. So it will copy what we supply to the program into this buffer space. So if we copied Nancy, we wrote Nancy or passed Nancy to the binary, it gets copied to the buffer and the buffer gets printed out back to us. Perfect. So that's a classic standard buffer overflow attack. If we were to supply something huge, bigger than 128 bytes, which I'll just quickly show that to you right now. If we were to supply maybe a bunch of A's, let's say 150. Sorry, that's Nanya 2. You'll see that it tells us segmentation fault. So what essentially this means is that our program has crashed. And by the way, if you want to follow through this, or if I'm going too fast, you can check the guide that I've written on GitHub. It's basically the guide for this session, and you can see how we'll use those steps in exploiting this program. So now, we can head over to GDB using the command GDB, then we supply the name of the file. I think I've written most of these functions, the explanations in that guide. We have functions like, I think, info functions that list the functions that are being used by the program. You can see the main function, string copy, printf, the exit system call. And the main function is where the program is going to start, basically. And if we do a disassemble main, let's start by setting the flavor of the debugger. Let's do it Intel, I guess. So let's disassemble main. What this set disassembly flavor does, if you're to disassemble main just like that, you'll get maybe different intacs, like I think ATT or something else. I like to use Intel because it's more readable. So if you disassemble main, okay, we won't really dwell that much on the gibberish that you're seeing here. But just to summarize, we have the function prologue over here, which basically saves the base pointer and the stack pointer so that they don't get overwritten when the program is running. You can see printf being called on something. We can see the exit system call. We can see string copy as we saw in our program in the printf. So what you can do, let's use the command breakpoint. Breakpoint goes like this. You set a breakpoint on a certain memory address so that when execution reaches that memory address, it stops. You can use it to debug your functions and stuff like that. I think if we have any software devs here, maybe when you're working with frameworks like Django or Rails and such, we have, I think, debugging libraries that can help you set breakpoints in your code such that the code stops there and you can pop a shell or a console and you can debug your functions and stuff like that. So that's basically the same thing that's happening here. So if you paste this here, set a breakpoint and run our program, okay, it needs an argument. So you run it with something, maybe several A's. So the program will run, and before the main function returns, it hits the breakpoint. And at this point, we can start to view what's in the registers with info registers. So info registers shows us the registers we have in memory. You can see the stack pointer. So this is the address of the top of the stack. Right now, the base pointer doesn't have anything. We can see the accumulator doesn't have anything, and the instruction pointer. So something to note here is that if you look at this address, the instruction pointer, it's pointing to the next instruction to be executed in memory. And the next instruction basically to be executed will be the return function, because we set a breakpoint here, meaning we won't execute this function. So if you look at this address and you look at this address, you'll see that they're the same. Meaning, if I were to continue by pressing C, we would return now. So we basically hit the return. I don't know if we can view registers at this point. Yeah, you can't view registers when the program isn't, I think, running. So let's run this program and actually crash it within GDB. So we used R and then we passed something. So this time we pass a large input. So this command that I'm doing here is basically like, I think it's basically executing this Python command that we supply here. Let's supply 150 A's and see what happens. So we hit the breakpoint, and if we continue, we see something interesting. We receive a segmentation fault, and this value that you see here is a value of the EIP. So why is the program crashing? The program is crashing because our A's have actually reached the EIP. And when they reach the EIP, let me just show you something real quick. If you do a \x41, does it need to be in, yeah. If you do a \x41, you'll see that that's A in hex. So our program is basically crashing because we have A's going into the EIP, and because this memory address doesn't exist in memory, the program will crash. It doesn't know what to do from there. So we get a segmentation fault error. Can we view registers? Yeah, we can view registers. So now that the program has crashed, we can try investigate further and see maybe what's happening to the stack. Let's start from there. So to see what's happening in the stack, we simply examine. X means examine. 40 means, or maybe 100, you can do 100, and then WX. So this means examine 100 words in hexadecimal. I think a word is 2 bytes. I think it's 2 bytes, if I'm not wrong. So we examine 100 words in hexadecimal, starting from the top of the stack. So from the top of the stack, you can see that there is ziliingia hapo, they entered the stack. So in specific, this is a stack-based buffer overflow. So what do we need to do to actually exploit this program? So what you're going to do is try find the location of the EIP in memory. If we know the exact location of the EIP in memory, we'll be on our way to actually controlling what this program is going to do. We can control it and make it maybe give us a shell that we can run commands on our target. So to do this, Metasploit comes in. We have tools in Metasploit. The first one is called MSF pattern create. And you remember we started by generating 150 bytes that crashed our program. So we know that the program crashed between 1 and 150 bytes. So we'll use this Metasploit tool to find the exact position of that override. It's 1 and 150 bytes, but how many exact bytes do we actually need to crash the program? So what Metasploit does, or rather this pattern create does, is it generates a cyclic pattern of bytes. And okay, how do I put this? The value that we'll find in the EIP, okay, say we give our program 150 A's. say we gave our program this on 50 A's, and the EIP tells us that this value is somewhere inside this A's, that this A's that tunaona hapa, these 4 A's are somewhere inside here. Will you be actually able to tell where these 4 A's are? Those A's could be this, they could be this, they could be this, they could be anything. So we don't know exactly what those A's are. But if you look at this cyclic pattern of bytes, you'll see that no 4 bytes repeat themselves. It's cyclic. It goes in a cyclic manner. We don't have repeating characters here. So if the EAP gave us this value, we would know that it is here, and we have this exact number of bytes to actually reach that value. So I think that point is gotten across properly. So if you run the program with these bytes, and we hit this breakpoint, press continue, and we hit this value. We try finding this value. And we get an offset. So we have pattern create and pattern offset. So offset, using this switch Q or tag Q, basically uses the value that you found in the EAP and finds it within your bytes. So right now, what it's telling us is that maybe these bytes are these ones, and we have exactly 132 characters to reach those bytes. So now that we have 132 characters before the instruction pointer, we can prove that we have control of the instruction pointer by adding 4 more bytes. Remember, this is 32-bit. Each register holds 4 bytes of data. So we can try add 4 more bytes to overwrite the value at the instruction pointer. So this is the value at the instruction pointer, but let's prove we have control. We'll do that by printing 132 characters and add 4 B's. So B in hex is 42. Remember, A was 41, so B is 42. So if we have 4 B's, and give our program that, we hit 4242 4242. So that proves it. We have control over the instruction pointer. Okay, so now that we've put 4 B's here, B's don't really mean anything. We need to make use of that. We need to make use of that value, or this instruction pointer rather. So what I'm going to do is put this into an exploit script. I hope struct module doesn't fail me this time. Okay, I was working on this previously, so I'll just erase it, start from this beginning. So we import struct, and then we have a padding. Our padding is how long? It's 132 characters long. And we also have an EAP value, which we set it to B's. And then for now, we're keeping it simple. We just print the padding plus the EAP. So yeah, we have that. And what we can do is open the file in GDB again. And when you run it, we supply, we don't have to do that. We can still do it how we are doing it the first time. Okay, perfect, it works. So we still get the segmentation fault at this non-existing memory address. Okay, so how do we put this into actual use, into something that we can actually turn it to our advantage? What you're going to do is execute some malicious code. We call it shell code, and I'll show you, I think, in the slides later. But where do we execute this shell code? We place this shell code inside the stack, so that if you are able to redirect execution flow to the stack, the program will continue and actually execute our shell code. So to place it into the stack, we need to know the memory address of the top of the stack, because that's where the shell code will enter. So if you do info registers, you saw that this was the address of the top of the stack. We can also do a print ESP and it gives you that. So now that's the value that we use at the top of the stack. But in this case, remember that the concept I showed you about little Indian and big Indian. So if you're to do a ls CPU and grep for byte order, it needs to be in caps maybe. You'll see that it's little Indian. So we pack this in little Indian in our exploit, and hopefully we'll be able to hijack control and take it to the top of the stack. So now, instead of having these, which are a bit useless in our code, we'll have that. Okay, we won't have that. We'll pack it in bytes in little Indian format. We'll pack it like this. Perfect. So, okay, let me confirm that it doesn't give us any errors. Good. Okay, so now let's go back to GDB and run. Okay, before we actually run it, let's set a breakpoint at that particular address of the stack, that's the top of the stack. If we set a breakpoint there and we hit that breakpoint, we'll know that we've directed our execution flow to the top of the stack. So I don't know if it will give me the address or I still have to run this. Oh, I have this copied already. So you can break to this address. And then we run our program, supplying that file that we are writing our exploit in. Perfect. You see this? This means that we've hit our breakpoint. So our control flow has been redirected to the top of the stack. So let's make use of this. So we inject shellcode now. Instead of injecting, right now we aren't injecting anything. So this time we inject shellcode. But before we inject the shellcode, let's go back to the slides and I show you something interesting called an OP-SLED. Okay, so what an OP-SLED does, an OP-SLED is this kind of fail-safe method that what NOP means, NOP means no operation. So if our compiler hits, if our compiler hits a no operation, it simply just continues. It continues moving, sliding along the addresses in memory. So if we have maybe 5 NOPs and then we have our shellcode and our compiler encounters a NOP-SLED, it slides down the NOP-SLED and reaches our shellcode. That's what the NOP-SLED does. Shellcode is the code that you want to execute to gain a shell. So why do we need a NOP-SLED? We need a NOP-SLED because if we are writing our exploit using GDB, remember that GDB is also loading up its own functions that it needs to actually show us what it's showing. So it might mess up the addresses. The addresses that you see appearing in GDB isn't exactly maybe the same how it will appear outside GDB. So we need an OP-SLED, and we will redirect our execution flow to the OP-SLED and slide down safely to the shellcode. So to do this, don't worry, I'm almost done. To do this, we will put our OP-SLED here, and we'll use the \x90. That's an OP-SLED. We'll use 100 of those. So now, if you're using 100 OP-SLEDs, we need to adjust the size of our padding. We need to adjust the size of our padding such that, or rather the exploit. I think I should just put this here. Exploit equals to the padding plus the EIP, the NOP sled plus the padding plus the EIP. So if we hit this address, we go to the top of the stack, right? But we want to maintain this size. We want to maintain a size of 132. The padding, the exact exploit should be a size of 132. So we are going to subtract the size of our NOP sled. So now we'll have exactly 132 bytes, and then we will examine it again in GDB and see where exactly we want to go. Let's take a way down. Oh, should be an offset, sorry. Oh, I'm not following the board mass rules. Is this okay? 1, 2, 3, 1, 2, 3. Yeah. So we head over back to GDB and run this again. Nice. So we still hit the top of the stack, meaning our size, the size of our payload is accurate. We have this exactly 132 bytes before we reach the EIP. So now let me show you what the stack looks this time. I'll offset it by -200, so we see maybe a little bit behind the stack how it looks like huku nyuma. See, the stack is starting from around here. And what we want to do, instead of using this address, we use an address that will actually get us between the NOP sled, an address that will land us here and then slide down to our shellcode that we will be injecting. So now let's pick an address, a random address like this one maybe. We go back to our exploit, and then our EIP this time will fall on that particular address. And then after the shellcode, after the NOP sled, we'll have a shellcode. So you can head over to Shellstorm. I'll try to hurry. We'll head over to Shellstorm and copy a shellcode that we can directly use. Let's strip out this quotes and then put it there for us to use. Good. So we'll hit the NOP sled, then we hit the shellcode. So we add this to our code, add the shellcode, and then you adjust the exploit. So 132 minus the length of the NOP sled minus the length of the shellcode. So let's try run that again. Okay, so if our exploit works correctly, we should get a shell. So let us try run this as an argument to Okay, we don't get a shell. So we probably need to adjust the address where we actually hit the NOP sled. Because when the exploit gets out of GDB, what usually happens is that it gets slightly adjusted. It gets slightly adjusted and the components move upwards. So you might hit the wrong address and you have to keep actually changing till you get the correct address that you're supposed to actually fall on. So we can go back to our, I think we can go back to GDB and adjust our exploit to actually fall on that correct address that we need. So we don't have, we're not supposed to get a segmentation fault. If our code works, we land on the shellcode and, oh, you see, it works in GDB, but it doesn't work outside GDB, which is a problem. So we need to fix that and adjust it in a way that we'll actually reach the shellcode outside GDB. Our exploit has to work outside our environment. Ooh. Okay, can't work outside the stack. Okay, so let's adjust the exploit manually. Okay, so this time we're landing on FFD5D8. We need an address that is, I think, slightly higher so that if our exploit gets shifted to a higher address space because we are removing some components at the top, which are GDB components, we land on the NOP sled. So we can move downwards a bit to 640 because you're going downwards the stack. Perfect. So we hit the shell code and we get a shell. And we get a shell as the effective ID of the Narnia 3 user. And for this challenge, you're supposed to find the flag for, I think, the Narnia 3 user, which is the password to the next level. That's how the over-the-wire war games work. You find a password and it takes you to the next level. You have to exploit that level, get the password for the next level. So you can find from the root, find a file, and we find a file with Narnia 3 in it. Redirect all these errors to dev null. And we get the password for the next level here. So I think that's an introduction. I wouldn't say easy, but maybe relatively simple to other exploits, low-level memory exploits in buffer overflows. The last part was to cover mitigations, but because of time, I'll brush through. We can mitigate against these exploits using things like ASLR, NX. NX means that we can use some kind of code that prevents us from writing code into the stack. So my code would fail if there was NX enabled, and we'd have to use things like return-oriented programming to circumvent things like NX. We have ASLR that randomizes the addresses in memory. So the top of the stack, you remember it was a particular address. So in other cases, we might not even get that address because it will be randomized. We have things like pi position independent, I think, executable, I think, places this random bit inside the, sorry, that's canary. Canary places a random bit inside the, maybe the stack or somewhere in memory. And when you try to inject code, it detects that what you're doing is illegal or something like that, and then gets flagged. This one is sort of similar to SLR. So I guess that marks the end of today's session. Thank you all for coming. We had issues, I think, during the first part of the session, but we were able to finish properly. If you have any questions, you can drop them on the chat. So yeah, this is over.
Okay, thank you so much, Trevor. It was so involving, very, very practical and technical. I'm sure each and every one of us here has learned something. Thank you once again. So I think if you have any question, maybe you can just type it in the chat box and Trevor will get back to you. Yes, thank you. It was super amazing. Thank you. If there are any questions, just type them in the chat box and Tony or I can read them out, and then Trevor can get back to you. Thank you.
No questions for now.
Okay, well, I can't see any questions, just comments. Someone has suggested we add 30 minutes to the normal one. How? Okay. Okay, I can't make that decision, but it can be put into consideration. It was an awesome session. I think you were so thorough. It was thorough. You explained so well. Okay. I don't know if anyone has a question. Now is your chance to ask anything maybe you might not have understood. Just type it in the chat box. Okay, there's a question. Okay, comment, a well-executed session. There's a question from Steven has asked, where does one get to learn this more? If you have links, yes.
Oh, I'm pretty sorry for not actually compiling a list of good resources that you guys can go use, but I'll quickly write some on the chat, like pwnable.kr. We have Rope Emporium, ROP Emporium, go to Over the Wire, of Protostar, and CTFs. CTFs, I think, are the best way to learn some of these things. Like Koimet usually says, when doing, I think, bug bounty, most of the bugs he's come across, he met them while doing CTFs. So if you play CTFs, you'll encounter most of these things and get to learn a lot along the way.
Okay, thank you. You can check the chat box. He has highlighted some of the resources that you can use to make you better at this. Okay. Stephen, I said thank you. So I don't know if there's any other question. If we don't have another question, maybe Tony, you'll say something and then, oh, we also have Eve. Eve is also on call. So maybe I'll give the chance to either Eve or Tony to say something and then maybe we can close the meeting.
I can go first and then I can let Tony pick up. So thank you so much. So I believe I still have something I need to share with you. On the side. Thank you for the session. I've really learned a lot myself and I believe everyone else. And thank you for the different participants that are here for turning up for this session. Yeah, we look forward to the next one. And thank you, Nancy, for organizing this for us. And over to you, Tony.
Oh, yeah, thank you, Eve. I've not forgotten about my package.
Okay, Tony. Tony maybe would say something and then maybe we can close the meeting.
Wait, we have a question at the chat. Someone asks, if the stack is not executable, Then what do we do? Well, if the stack is not executable, that means we can't inject our own code to execute. So what we do, we use the code that our program actually has. There's something called libc. You can look more into that. You use libc and circumvent some of those tactics. You can get things like the system command, or maybe bin-sh somewhere inside your program and use that to gain a shell or something. So that's what return-oriented programming is about. If you look at the challenges from ROP Emporium, you'll see that you won't be able to execute any code on the stack. You'll have to use something called return-oriented programming. It's a really interesting concept. You can look at it, the Tech Guru.
Okay, thank you. Thank you so much, Trevor, for the insight. I've also learned so much. I think I'll say maybe I'll close, just finish up. Thank you everyone for attending this session, and we're so happy that you attended this session. We're hoping that you've learned so much. And you can also, in case maybe you want to revert and maybe learn something, or maybe something you might have missed out on, we have a YouTube channel. You can check it and maybe subscribe to be notified anytime we go live. And well, with the next session, we'll have the community edition session on Thursday. Join in for that one as well, and for the campus edition again next week on Tuesday. So thank you once again for attending. And yes, I think we're done. I think we'll just come to the end of the meeting. Thank you once again. I wish you everyone a blessed night. Good night.
Good night, everyone.